Guys, okay. Last lesson of the chapter. As always, this is a brutal week. I know it's a lot, but we are on track to finish 3 chapters. Right, we've got all next week to kind of slow down and do lots of problems, extra zooms, all that stuff. So let's finish up strong here. So these last 2 topics. The good news is this idea of linearization. Really, what I want you guys to think about is we're going to find a tangent line and plug in to that line. Okay, and so let me just kind of give you an idea of what's happening. So this idea of linearization is, let me get some scratch paper here. So the example down below talks about the square root of x function. And so what we're going to do is we're going to say, we know some stuff about the square root of x function, right? We know that it looks something like that. Okay, that's the function y equals the square root of x. Well, what if I asked you to find the square root of 4.2, right? Without a calculator. Because if I had a calculator, it's super easy. I type in the square root of 4.2 and you get your exact decimal to however many places you want. But what you're going to be able to do with calculus is get ridiculously close to this correct value without using a calculator, which is kind of embarrassing because we're going to be considered to be ridiculously smart now without a calculator. So what are we going to do? Well, do you know what the square root of 4 is? Yeah, sure. 1, 2, 3, 4. We know that the square root of 4 is 2. Okay? And so what we're going to do is we're going to use that point, 4, 2, to come up with a tangent line right there. Okay, so we're going to get the equation of that tangent line, which we always call y sub t. And then what we're going to do, you guys, is we're going to plug in 4.2 to the tangent line. So we're going to come right here to 4.2, and I'm going to plug it into that line, and I'm going to get an answer that's not perfect, but it's ridiculously close. Okay, so let's do it. So this first part of just this word linearization, we're literally going to find the tangent line and then plug in to use it. So it says, find the linearization of this. That is a fancy word to find the tangent line. Okay. And then use it to approximate 4.2 without a calculator. This is a typo. This should say at x equals 4. Okay. From the picture I drew, that's what we're going to do. Okay. So let's do it. So we've got f of x is equal to x to the 1/2. And so I know f prime of x would be 1/2 x to negative 1/2, or 1/2 square root of x. And so if I'm looking for the tangent line, I know I need a point, 4, 2, right? Because it said at x is 4. When I plug it in, the square root of 4 is 2. And I need f prime at 4. So I have my f prime right here. So f prime of 4 is going to be 1/2 square root of 4, which is just 1/4. So I think hopefully you guys can realize why I'm plugging in 4, right? I'm plugging in 4 because I know the square root of 4 without a calculator, right? That's why this worked out nice and neat. And so really what we found is this tangent line, okay? But notation that they might use is this L of x, so this linearization. Okay, so don't be freaked out. It's exactly the same as a tangent line. All we do is we say, like always, it's the y value, which is 2, plus the slope, which is 1/4, okay, times x minus the x value of 4. All right? And so what did we do? We just found this guy, okay? So now how do I use that? Well, let's find the linear approximation at 4.2. It's going to be equal to 2 plus 1/4 of 4.2 minus 4, which is 2 plus 1/4 times 4.2 minus 4. This is simple stuff without a calculator. You get 0.2. Hopefully you guys know that 0.2 is 2/10. Might have been a while, but that's where we're at. And then I can say, well, that's 2 plus, well, that reduces to that, and you get 1/20. Okay, so 2 plus 1/20. Now, as an answer, maybe you get a common denominator, and you say that's 40/20 or 41/20. Okay, that is our estimate right? L of 4.2 is equal to this value, okay? And we did all of that without a calculator. So from before, I told you, if we had a calculator, we would just plug in 4.2 and take the square root of it. Well, we didn't. And we found that approximately it would be 41 divided by 20. Yeah. And so you are embarrassingly smart and can now approximate random square roots using calculus, getting within 1/100th of the actual value or less, which is a really, really good estimate. Okay. All right, let's look at the next one. So the next one is trig. And so, that's the only reason this will be more complicated is because it's a trig function. So we're going to do the same thing, though. We're going to find the linearization, which is a fancy word for the tangent line, at pi over 2. And so if you want to have cosine at pi over 2, right, to find your y value, plug in cosine of pi over 2 is 0. So we have our point. We also need f prime at pi over 2. Okay, so we have f of x is given as cosine. F prime of x would be the derivative of cosine, which is negative sine. And f prime at pi over 2 would be negative sine of pi over 2. Well, sine of pi over 2 is, remember, up here. That's a value of 1. And so negative 1 would be my answer. Okay? And so what we're going to do is we're going to say that our linearization model, right, which is fancy for tangent line, is just that, tangent line. So it's the y value, which is 0, plus the slope, but the slope is minus 1, times x minus the x value, which was pi over 2. Okay, so we can kind of clean that up, and it's just negative x plus pi over 2. Okay. All right, so they want to estimate cosine of 1.75. And so I would say, well, the linearization model at 1.75 is equal to negative 1.75 plus pi over 2. Okay. And so how far do we want to go with this? Well, we should probably just get another estimate. If you assume pi is rounded to 3.14, right, you're supposed to come up with pi over 2. Okay. And so if you did that, you would do half of pi, which would be 1.5 plus half of 0.14. So we're going to just say that this is approximately 1.57. Okay. And so if you do 1.57 and you add in the negative 1.75, right, we can do that, some mental math there, and get negative 0.18. Okay. And so what we're saying is that, look, we don't have a calculator. We still have to do some annoying math there, but we rounded it, right? This is an approximation. And so we're saying that it's approximately negative 0.18. And so if you come in here and you type in cosine of 1.75, negative 1.78. So we are really, really, really close. We're off by 2 thousandths. Okay, so again, this hopefully doesn't intimidate you, because really all you're doing is finding a tangent line, and then you're not only finding it, right? We haven't plugged into a tangent line before, but now we're just plugging in a numerical value to come up with our estimate. Okay. All right, looking at the second page of the notes, the next part are, they're very similarly related, but I'm not going to go into why, because it could make it seem a little bit more difficult. So differentials are the little parts of dy dx. And so let me just do a random example up here. So to kind of desensitize your brain, if you have y equals 3x squared, I think you guys know dy dx would equal 6x. Okay, so what we're talking about here is this little guy and those little guys. Those are what we call differentials. Okay, and and so what the d, right? You guys remember the delta in math? That means the change in. Well, this is very similar, but it's an estimated change. So this just means, look, this little change in y and this little change in x is equal to this. And so I could use these independently, just like normal algebra. So if I wanted to get the dx on the other side, I could say that dy is equal to 6x times dx. So we can actually split these pieces up and use them independently. Okay, So it tells you here that let y equals f of x be a differentiable function. The differential dx is an independent variable. The differential dy is this. So remember, the step before here was dy dx is equal to f prime. And then all they did was they separated it, right? They multiplied both sides by dx to get it. Okay, so that all being said, what the heck are we doing? So what we're going to do is we're going to take the derivative of this function and we're going to separate our differentials, and then we'll talk about what that means. So let's just jump in and do the derivatives that we know how to do. It's pretty simple stuff here, just power rules. I know I would get dy dx is equal to 5x to the fourth plus 37. That's just the derivative. That's nothing new. Now we know we can split these up. So I'm going to solve for dy, and I'm going to say dy equals 5x to the fourth plus 37 times dx. Okay? So this is the estimated change in y. This is just your x value, and this is your change in x. Okay? And so all we're going to do is we're going to use this, and we're going to say evaluate dy. That just means find dy. Okay, well, we have it. Dy is right here. Dy is going to be equal to 5 times the x value they give you. You just plug in. That's 1 to the power of 4 plus 37 times dx, which they gave us as 0.01. Okay, we can use a calculator on these problems. This is very simple. This is just equal to 42 times 0.01. A lot of you can just do that in your brain. If you can't and you don't want to think about decimals, just multiply it, right? You know that that's going to move it over 2 spots to give you 0.42. Okay. Okay, so what did we just say? We said that given this function, if you change x by 0.01, the estimated change in y is 0.42. Okay, so it's just another estimate. Okay, and we'll get into kind of some examples a little bit later, but let's keep practicing how to do it. So we know to use differentials, we take the derivative. So we get dy dx is equal to the derivative of sine is cosine of 3x, but don't forget chain rule, times the derivative of the stuff, which is 3. And if I solve for dy, I get dy equals 3 cosine of 3x all times dx. All I'm doing is I'm splitting out this derivative part that we thought had to stay together until today. And so I can come up with a dy value, an estimated change in y, at a particular place. So if I plug in pi, and then I multiply by the dx value, which is negative 0.02, okay, I'm going to get, well, cosine of 3 pi. So it's all the way around circles 2 pi, one more, that value is negative 1. So I get negative 3 times negative 0.02, right? 2 negatives make a positive, and I'm going to get 0.06 is my answer. Okay, so dy is that. Okay, so my estimated change in y, if I change x, so if I, instead of being at pi, what if I want to go to pi minus 0.02? What's my function value going to be? Well, it's going to go up by 0.06. Okay. All right, one more, and then we'll look at the word problems on the next page. So let's take the derivative here. This is not solved for y, so we need to use implicit differentiation. And so we're going to take the derivative piece by piece. The derivative of x matches x, so it's just 1, plus the derivative of y is just 1, but since they don't match, you have your dy dx equals, over here we have to use the product rule. This is first, times the derivative of the second is dy dx, plus the second, which is y, times the derivative of the first, which is 1. I know I have to solve for this, so let's get these two terms on the same side. I have dy dx minus x dy dx equals, there's a y on this side, and then you have to subtract 1 over here to get that there. Now I can factor out my common term, dy dx. times 1 minus x equals y minus 1. And so I get dy dx is equal to y minus 1 over 1 minus x. Okay, so that was more complicated because we had implicit, but now the game is the same, right? Solve for dy, so I know my estimated change in y is going to be equal to y minus 1 over 1 minus x times the dx, so I can move it over to the other side. And now all I do is I plug in. So I can say, look, my estimated change in y is going to be what? Well, look, I have x, okay? I've got dx, but I don't have this y value. And so you have to do a little bit more work here. So let's plug in x to our equation. We get 2 plus y equals x is 2, so 2y, or 2 equals when I subtract y. Okay, so I've got x is 2, y is 2, so 2 minus 1 over 1 minus 2, times the dx value of 0.05. That's 1 over negative 1, so negative 0.05. Okay, and so differentials just gives you a way to estimate a change in a y value given a particular change in x. All right. Okay, so let's just look at this next page and chat about it. I'm going to probably pause at this point. I'll do 2 different videos for this lesson because I want to do a quick review on the part 2 that you can come back at. Go take a little break, get yourself some ice cold water or something, and a snack, and then come on back and we'll recap what just happened, and then we'll apply it using these 2 different equations. Okay.